Hello and welcome to the lesson 7.5 video. Today we're going to look at conditional probability and independent events. And you might want to have your 7.4 notes because we're going to be referencing the rolling of the two dice table and also the cards, if you're not familiar. So example 1 is all about this conditional probability. So conditional probability is the probability that an event E happens given F already happened. So the probability of E happening given that F happened. Okay, that's how that's read. And we can find that if we know the intersection of E and F, and if we know the probability of F. So if a single die is rolled, find the probabilities of the following results. So this is just a single die. So there's 6 possibilities on a single die when it's rolled. What is the probability of getting a 2 given that the number rolled was an odd? Well, that is 0 because if you rolled an odd, it could not be a 2. So that is that. It's really just 0. What is the probability of an even number that you've got an even number given that the number rolled was 6? Well, if you rolled a 6, then it can only be even. So that's 1 or 100%. Now let's look at when 2 dice are rolled. So given that 2 dice are rolled, find the probabilities of rolling the given sums. So a sum of 8, given that the sum of is greater than 7. So given that it's greater than 7, that means it would have to be 8, 9, 10, 11, or 12. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So out of the 15 possible, what is the likelihood of getting the sum of 8? So the sum of 8 was 1, 2, 3, 4, 5. 5 out of 15 or 1/3. So when you have the outcome to the count, you don't really always need the formula up above, but we're going to use it later. What is the probability of a double given that the sum was 9? So given that the sum was 9, there's 1, 2, 3, 4 ways we can get a 9. But of those 4 ways, none of them are a double because it's an odd outcome. So that would be 0. The product relation of probability. If E and F are events, then the probability of E and F may be found by either of these formulas. So the probability of E and F, so the intersection, is equal to the probability of F times the probability of E given F, or the probability of E given F, I'm sorry, E intersection F can also be found by the probability of E times the probability of F given E. So you have to know these 4 situations, either these 2 or these 2. So let's look at 2 cards. So it says 2 cards are drawn at random with replacement. Yours says without replacement. This should be without replacement. We're not putting the card back in. So with replacement means we're drawing a card, we're putting the card back in the deck, and we still have 52 cards. Without replacement means we're dealing the card out, setting it aside, and now we're dealing another card, but we only have 51 cards to choose from. So it says, what is the probability the second is a heart, given that the first is a heart? So given that we know that the first is a heart, there's 13 of those. So we know this is out of 13. And because it was without replacement, and the first one was a heart, we know that it is sorry, there's only 51 that it was a heart, given that it was the first one was a heart. There's only 12 left out of 51. So once we know that the first one was a heart, the second one being a heart, it's going to be 12 out of 51. And that is 0.235, oh, 3 if we round appropriately, 0.2353. Then the next one says, what is the probability of a jack and a 10 are drawn? So we could have a jack and then a 10, or we could have a 10 and then a jack. And they're going to be the same probability, so we're just going to be adding the same probability twice. So a jack would be 4 jacks out of the 52 cards. We're going to set that card aside, and then we're going to draw again. And then that means that there's still 4 10s available, but we only have 51 cards to choose from because we set the first one aside. That comes out to be 0.006. If we look at the other way, if we draw the first card and it's a 10, there are only 4 of those to choose from. And then when we go to draw the second card, there's only 4 jacks. Those still remain because the first one was a 10, but there's only 51 cards. That too is 0.006. So when we add them, it is 0.012. So let's look at example 4. I like tables because tables kind of have most everything you need right there. Says the Midtown Bank has found that most customers at the teller's windows either cash a check or make a deposit. The following table indicates the transactions for one teller for one day. So the person either cashed a check or they did not cash a check, or they made a deposit or did not make a deposit. And they could cash a check and make a deposit at the same time, or they could not cash the check and they could make some other deposit, or they could not cash a check and then not make a deposit. They could be coming for something else. So let C represent cashing a check and let D represent making a deposit. Express each probability in words and find its value. So I'm going to read them to you and then find its value. So the probability of C given D. So the probability of cashing check given they made a deposit. So given that they made a deposit, we're looking at all of the deposits, and there's 80 of those. So out of the 80 deposits, what number of them did they cash a check? That would be 60. So that reduces to 3/4. The next one says the probability that they did not make a deposit, given that they did cash a check. So given that they did cash a check is out of 90, the total here, and that they did not make a deposit, that was 30 of them. So that is 1/3. And then the last one says, what is the probability? And it's the probability of the complement here. So don't forget there's a complement here of the intersection of C and D. So would be they made a deposit and they cashed a check. So cash and made a deposit. That would be 60 out of the total 120, because that's the total. So 60 out of 120 is 1/2, and we want the complement of that. So that would be 1 minus the 1/2, which is still 1/2. We're also introducing independent events. So independent events are an event is considered independent of one another if the occurrence of event A does not change the likelihood of event B. So A and B are independent if the occurrence or not occurrence. It does not affect, does not change the likelihood of B. B does not depend on A happening. And not that it has to happen to make B happen, but let's say this, if I were to be driving 90 down the highway, I am changing the likelihood of myself getting in an accident. So those are dependent events. It doesn't mean if I drive 90, I'm definitely getting in an accident. It just changes the likelihood. Okay, so events E and F are independent if the probability of F given E is equal to F, or the probability of E given F is equal to E. Also, the events E and F are independent if and only if their intersection is given by their product. If you multiply their individual probabilities together and they don't equal the and or the intersection, then they're not independent. So let's look at a few examples. So example 5 says that A and B be independent events with the probability of A is 1/4 and the probability of B is 1/5. What is the intersection? Well, we know they're independent, so we can then calculate their intersection by multiplying them together. And we get 1/20. What about their union? So their union would be the probability of A plus the probability of B minus the probability of A intersecting B, which we just found. So this would be 1/4 plus 1/5 minus 1/20. And if we get a common denominator of 5/20 plus 4/20 minus 1/20, we have 5 plus 4 is 9 minus 1 is 8/20. And we can reduce by a factor of 4. And we arrive at 2/5. We'll take a little thinking about here. If A and B are events such that the probability of A is 0.5 and the probability of the union is 0.7, find the probability of B when they are mutually exclusive. So when they're mutually exclusive, we know that the probability of A intersecting B is 0. We learned that in a previous lesson. So when they're mutually exclusive, they cannot happen at the same time. Their intersection is 0. So that means that we can use the union rule, A union B, because then if they're mutually exclusive, then we can just add probability of A plus the probability of B. Well, we know the union is 0.7, and we know A is 0.5. So subtracting 0.5 from both sides, we can find out the probability of B is 0.2. For that scenario. Okay, so for getting the mutually exclusive, we're just going to say now find probability of B when A and B are independent. Okay, so if they're independent, we know a few things. We're going to go to that union again. So let's draw the union because that's what we've been given. So we kind of have to work with that. The probability of A union B equals the probability of A plus the probability of B. We don't know if they're mutually exclusive. So we have to subtract any intersection. Okay, so we know the probability of the union is 0.7. We know A is 0.5 plus the probability of B minus, we know if they're independent, this intersection is going to be the probability of A times the probability of B. And probability of A is 0.5. Okay, so let's subtract out the constant, which we don't need, the 0.5. So we have 0.2 equals probability of B minus 0.5 times the probability of B. So if we factor out the probability of B, we will have 0.2 on the left. We're going to pull out our probability of B, and then we have left 1 minus 0.5. And 1 minus 0.5 is 0.5. And so we can divide both sides by 0.5 to solve for the probability of B. Haven't done a little algebra in a while this semester, so this is fun. So 0.2 divided by 0.5 is 0.4. Okay. Example 7 says, according to a recent report, 68.3% of men and 64.1% of women in the US were overweight. Given that 49.3% of Americans are men and 50.7% are women, find the probability that a randomly selected American fits the following description. Okay, so what we do know is we know, let's go down here. Man and woman, so we know 0.493 and 0.507, those add to 1. And then it says 68% of men are overweight. So we have overweight and then not overweight. And we're going to have overweight and then not overweight. Okay. So we have 64.1, 0.641 of the men are overweight. And then we know, oh, that was the women. 0.683 of the men and 0.641 of the women are overweight. Okay. So let's look at the questions here. I'll let you look them over. An overweight man, and then just being overweight altogether. And then are the events male and female independent? Are the events being male and overweight independent? Okay. The way I wrote my percentages didn't accurately. We're saying that 68.3% of these men are overweight. So because they're we're going to just multiply those probabilities together because that's how we find one given the other. So the probability of being overweight given they're male is by multiplying them together. So that is going to be 0.3367. And so that is an overweight man. Overweight given they're male. That is 0.3367. Okay. Then they want to know the probability of just being overweight. So just being overweight, we'd have to know both situations. So we'd also have to know the probability of being overweight given that they're a woman. So if we multiply the probability of being a woman, and then 64.1% of those women are actually overweight, that means that 0.3249 here. So when we add these together, this is 0.3367 plus 0.336. Oh, sorry, 0.3249. We get 0.6617. And then it says, are the events of being male and overweight independent? And that is no, because the probability of being a man times the probability of being overweight. Let's use the other one. Because the probability of being overweight, given that they're male, if they are independent, let's remind yourselves of this. If they're independent on this page here, then the probability of being overweight given they're male and overweight given they're male should equal the probability of being overweight. And they're not. They're not the same. Being overweight is because being overweight changes depending on if they're men or women. That's essentially how we know here. We haven't learned enough just to find the probability of being overweight overall, but they did tell us that given that they're men and given that they're women, we know their percentages. The last example, 8 here. A medical experiment showed that the probability that a new medicine is effective is 0.75. The probability that a patient will have a certain side effect is 0.4, and the probability that both events occur is 0.3. Decide whether these events are dependent or independent. So we know that the probability of effective is 0.75. The probability of a side effect is 0.4. And the probability that they both occur, that is E intersecting the side effect, is 0.3. And so if they're independent, 0.75 times 0.4 should equal 0.3. And it does. So yes, they are independent. Catch me back for the last lesson.